see a Tom bomb. Okay. Just a picture of us. All right.
This is a really
This
nice
who did it. All right, Byron, over there. Jace. Josh. Steve. And myself. All right. Our inspiration for this was, of course, you. All right, the goal of this, first of all, was design a bridge, of course. So ultimately, to be the lightest. We want it to be unique, be very aesthetically pleasing, and meet design requirements. Josh, can you talk about the design requirements?
As you all know, we all have the same design requirements. Minimum roadway width of 6 inches, minimum vertical clearance of 6 inches, maximum width and height of the structure at any given point were 12 inches and 9 inches. Same picture that we all followed. So, materials used were super glue, A-grade balsa wood, which is where the fibers run the length of the wood. So it was better for like tension forces. We couldn't find any of the ones that were best for compression. An X-Acto knife, a ruler, and a Dremel tool to sand it down so all the joints were squared up. Our design, we honeycombed / used intersecting members to create the bridge deck, which is right here. And there's a close-up picture of the bridge deck. Then we utilized the gussets to create more surface area for all the members to connect through and to glue on, and that gave better adhesion. We recognized that the cords would take compression and tension moments while the web structure was under the shear. And we wanted it to be aesthetically pleasing, added the coolness factor. We didn't want it to be too simple. So that's what our final bridge looked like. And we provided zero force members for redundancy in the structure, even though there was a point below. So we probably didn't need to add as many as we had, but we'll get into that later.
This is just going a little bit more in depth with design and design parameters. First thing we wanted to design the substructure was the first thing we were thinking about. Do intersecting members, therefore decreasing weight but increasing strength because of perpendicular grain that was running through it, therefore it being superfluous. Gussets were used, like we said, that would increase surface area for glue to be adhered, therefore increasing strength. Trusses were attached all the way to the bottom of the deck, also to have more surface area for the glue, but also to distribute the loads throughout the whole bridge. And then additional members were added to the bottom here and going up in the tension force here. And that was done because max moment is at the bottom, middle of the member, and also on the top as well for moment. The double layer Pratt truss, at first we originally designed it to just be one with big rectangles instead, but we realized that if it was a square it was going to be stronger, so then we made it 2 layers of the truss, or the frame within the truss. And then the last thing was we ensured that the bottom and top members, or the cords, were doubled up or thicker beams, because obviously they're carrying the moments, and then all the web within is in shear, but they don't have as much forces running through it, so we made those thinner. And next will be Steven's bridge.
After we built the bridge, the resulting weight was 419.8 grams, and it carried 109.6 kilogram load. Which is a strength to weight ratio of 261, which is about average. I think it plays 6 total, and it didn't deflect much, only 0.1 inches. So the resulting analysis from the bridge, the load path was distributed through the bridge deck and into the truss, causing large compressive forces on the exterior beams. The exterior beams pretty much stayed in contact with each other. Pretty much the bridge deck was what exploded, and on the inside, the honeycomb structure, it started shearing right on the inside. So as soon as any load was distributed through the frame, it started to shear, and And as soon as you put the load, you can start hearing it cracking. And it pretty much cracked the whole 5 minutes the load was applied on to the bridge. The result was a brittle failure. There was no deflection in the bridge structure. As you can see, this member is actually our densest member of balsa wood. We actually ended up, we wanted to run the whole length of the bridge, but we only had one piece, and we didn't have money, or the stores weren't open to buy a second piece. So we cut the piece in half, put one on one side and one on the other. The result was the load was distributed from the center to the ends, and it actually sheared right at that member. Otherwise, it would have broke somewhere in the middle. There's another picture. Failure also occurred at the intersection between the top and bottom trusses sections when the exterior beams broke due to hefty compressive forces. Oh gosh.
Say council.
And that was the result of the improper the gluing that we did with the super glue. Since super glue dries really fast, we tried to get glue on every single member within the honeycomb, but when we tried to put the bridge deck on, I don't know if you can see it, but if you look really close, there's almost no super glue attachment to the bottom structure. So the bottom half of the bridge deck was solidly affixed to the substructure, but not the top. And here's some improvements for future models.
The biggest thing for improvements would be to use a slower setting glue, because as you can see, the bridge deck is actually not glued at all to the top of the bridge deck, which caused it to fail a lot earlier than it should have. Kind of what Steve was saying, just apply the glue to the members to make it bond better to the top. The add members to intersecting substructure would just basically make the honeycomb structure smaller, which going back to like the third lecture when we were talking about maximizing the, I don't know what it's called, the strength ratio, it's doing the same thing here, it's just we do it a different way. And then of course reduce zero force members. As you can see, we had way too many zero force members for a point load. And then do different trials of the bridge instead of just doing one bridge would be another improvement we could do. And also just adding a beam that went all the way across the bottom of the bridge deck so it wouldn't shear right here.
See it. Any questions?
Any questions? Do we have time for a question or two? Is Matt Push up here? No, no questions.
Yeah.
How did y'all make that ladder structure? Then you just like cut notches in each of the pieces different way and just throw on top of each other?
Yeah.
Pretty much, it got drawn out in AutoCAD. Jason drew it out, and we measured out how far they need to go down, and one went down. We put the glue on, and then just cut a notch in it, and then the next top layer went over the top of it.
How many hours did it take you to finish the construction?
8 hours
8 hours.
at each, and we did it modularly. Josh and Jason worked on the substructure, and that took 8 hours to run, just in doing that. And then it took us about 20 minutes to put all the pieces together, but once we got that thing done,
There's a lot of cutting.
yeah.
Who made that kicking power?
Jason?
It was kind of my idea, but somebody told me about that. It's really easy to do if everyone figure it out. Gotcha.
So if you redo this bridge, would you go with the honeycomb idea again, or below?
Yeah, I think if we knew we could have gone below the actual structure because we thought we couldn't, then we would have definitely had a much stronger bridge. And then just
What
done.
kind of difference was it going to make?
It would have made it more like a moment diagram. So it would have happened. like if we would have been able to replicate what the model diagram looked like the one that was in a triangle. You're saying with just a slab? I don't know if I understand what you're saying.
So you were gonna do you were gonna replicate the moment diagram with
We're gonna
the
put
truss
stuff
system?
underneath it, right?
Yeah, put stuff underneath it.
Well, it's the same idea, right? You can put it top or bottom,
Yeah.
will work just the same.
I think to introduce slower setting glue,
Yeah.
because it was just mainly when we tried to put that big piece on top of the honeycomb, it was like, all right, each two people had glue in their hands that's like running across and passing in and stuck it on. If we had used like rubber cement or some different epoxy, we could have put it on, weighted down, let it sit for longer, and then attach it across the door.
And originally, we planned to have two deck layers for the sandwich boards. But we couldn't do it below it because we got the idea from cardboard. If you look at, like, when you ship something from UPS, they have, like, regular cardboard's one layer, but then if you look at the heavy duty stuff, it's a double layer. So it increases strength exponentially if you add more layers.
I really like this kind of analogy. Good job.